Hello and welcome to another video about the Keithley 2231A power supply here. This is just supposed to be a quick follow-up to my previous video. I'd just like to look at the Setpoint generation again and do a quick experiment on that, and then just do a few measurements to try and characterize the power supply performance and the accuracy. So what I would suggest, first of all, let's get some pen and paper and look at the Setpoint generation again. So first of all, let's just quickly review what we learned last time about how the set points for the voltage and current control are generated inside the power supply, because it may not have been immediately clear in the last video. So what you have for each channel is we have a microcontroller, which has in fact two outputs, which are PWM. So the signal here will look something like that. You've got your pulse waveform between 0 and 3.3 volts coming out of the microcontroller, and the duty cycle of that waveform is proportional to your set point voltage or current. This waveform then goes through a buffer. Now I'm not entirely sure what kind of buffer it is. It might be a Schmidt trigger or not. From the marking on it, I would assume it's not a Schmidt trigger, but I'm not entirely sure about that. So anyway, it's a buffer. So what it means is that after here you again have the same waveform with no real change at all. Again, 0 to 3.3 volts. This output then goes through a two-stage RC filter. Now the exact values here don't matter too much, but the net effect is that at the output of the RC filter you will get a more or less DC voltage, which is proportional to the duty cycle you had at the beginning. So if your duty cycle here is very close to 100%, you get close to 3.3 volt here, and if your duty cycle is close to 0%, you get close to 0 volts here. And this DC voltage is then fed into the control circuitry, which then generates constant voltage or constant current. Now just to go in a little bit more detail of why doing it this way, in my opinion, is not exactly great. So the duty cycle itself is really well defined. If you have, say, a 16-bit timer that generates the PWM in the microcontroller, you have a very good resolution, and the duty cycle itself is actually really robust. So even if there is variation on the clock for the microcontroller, the duty cycle itself won't change. So in that sense, using the duty cycle is actually a really good idea to generate a reasonably robust and precise signal. However, the problem comes in that in this conversion from your waveform, your pulse waveform, to a DC voltage, the actual voltage values here, the 3.3 volt and the 0 volt, matter. And the problem is that if this 3.3 volt supply here varies a little bit, or if the output drive of this buffer varies a little bit, your DC voltage will also vary a little bit. And my gut feeling is that although this waveform here will be very well controlled, in terms of duty cycle, the voltage you get out will actually be not as good as it could be due to duty cycle. So one thing I was thinking is, what they could be doing is they could actually have some sort of feedback loop, say from this point here, going back into the microcontroller into a DC input, and then using that to basically control that DC voltage. So they would adjust the duty cycle on the fly to generate a known DC voltage. And for that ADC they would be using the internal reference of the microcontroller. But that is probably slightly better than just relying on the supply voltage and the drive characteristics of the buffer. So what I would like to do is I would like to open up the power supply again and just inject a DC voltage, say at this point here, and drag this node around and see if the duty cycle changes in response. Because if there's some control loop, introducing an error here would cause the duty cycle to change. So I think we open up the power supply again and do this. Okay, the cover is open again, and this picture should look familiar to those of you who've seen the last video. Apologies for the camera angle and this cable loom in the way, but I can't really get a much better view from the tripod here. The microcontroller is hiding down below here, and over here we have those two buffers. If I remember correctly, the left one is for the voltage control signal, and that trace goes over here to the RC filter and then into the control circuitry. So the first thing I would like to do is just probe the output here to make sure that this is actually the voltage control signal, and then we'll see how we can feed something in here. Incidentally, I should keep my left hand in the pocket because over here we have the mains inlet, and me waving my arms around and touching things is probably not a good idea. So let's have a look at what we actually get at this point to make sure we are looking at the right thing. The output is set to 2.5 volts, so we would expect roughly 1.6, 1.7 volts at this point in the middle of the RC filter. So let me just get the probe in here, and indeed 1.3 volts. Okay, let's set the voltage to something else. Let's say to 4 volts. And that went up. So yes, this point is indeed for the voltage control. Now what I would like to do is say leave this set at 4 volts and feed in an external voltage, which is say 2.1 volts or so, and then look at the PWM signal that's on the left of this resistor and see if that changes. So first of all, apologies for not getting the power supply itself in shot. My setup here is in need of improvement. What I've got here is I'm generating a voltage on this power supply, which goes to this probe, which I can use to inject that voltage in the middle of the low pass filter and alter the output voltage. On this multimeter here, we'll see the output voltage from the power supply, which is currently set to 4 volts. And on the oscilloscope, we'll be looking at the PWM waveform coming from the microcontroller. And the idea is that if I inject my voltage and there is some feedback on the DC voltage coming out, then the PWM should change to try and compensate for that. So let's see what happens. So first of all, let me probe the PWM waveform, which, if I'm not mistaken, should be on this point here. There we go. That's our PWM waveform, and we can verify that we're looking at the right thing by changing the voltage. So I'm decreasing the voltage and the duty cycle goes down, and I'm putting it back to 4 volts, and it's where it was before. Now let's take this voltage here and inject it in the middle of that low pass filter. Alright, off we go. Okay, so what we see here is that the output voltage does change when I inject that voltage, but the PWM doesn't, which tells us that there is no feedback at all from the DC voltage back to the PWM. Now that's really fair enough, I suppose, but I was just curious to test if that was indeed the case. Speaking of case, I think it's about time we put the cover back on the power supply and do a few more experiments. As you can see, the power supply is now back in its rightful place on the bench, and I've got it hooked up to the oscilloscope and the multimeter here, and I'd just like to do a few very basic tests on accuracy and general behavior. So first of all, I'd just like to turn it on and see if we get any significant turn-on spikes or anything through on the oscilloscope. I've got this fairly long cable here, so I'm actually expecting to see something just from the magnetic field of the transformer, but I wouldn't expect to see any major spikes. So you see this little bit of ringing here, which is just a volt peak to peak or so, but that's really just from the transformer. But there isn't any sort of proper output turning on for several milliseconds or so. So let's just do that again. Slower time base, and yeah, again, there's nothing really to be concerned about, so that's quite good. So let's also have a look at what happens when we turn it on the switch here. Push this, and as you can see, it just settles to its value. Very nice and fairly slow. That's about 100 milliseconds or so, but there is no overshoot or anything, which is really nice, and you wouldn't really expect anything else because there is no load connected to it. Also, let's look at the absolute accuracy here. The specs for the power supply are for voltage 0.06% plus minus 20 millivolts setting accuracy. We're well within that. Let's just try a few different voltages, say 30 volts. This is again well within what it should be. Let's try something smaller, let's say 0.1 volts. It's taking quite a while to settle, but then again that's because there's no load connected to it, and it does have the capacitors on the output, so yeah, it just takes a while to get there. Again, this is 1.5 millivolts out, which is again well within spec, so from that point of view everything seems fine. Now let's do something a bit more fun and test it under load. So for this purpose I have this, which I fished out the electronics bin at work a couple of months ago, and well, it was some sort of constant current sink just for high voltage or something, and well, it has this very large MOSFET and a power op amp on it, and I just repurposed that to be a constant current sink on this very, very large and heavy heat sink. Just to give you an idea of the size, it's about as big as the power supply here. Anyway, the idea behind that is you input a voltage here on this BNC connector, and then this thing will sink a current that is proportional to the input voltage, which is set through this resistor here. So let me just hook this up and then we'll be back in a moment. Okay, I've got this contraption all set up, nothing is on fire as far as I can see, and we are ready to have some fun with it. Over here we have my poor man's electronic load that I just shown you. This power supply here, the 12 volts, are just supplying the op amp on the electronic load, and this power supply over here controls the current that is being drawn by the load. So if I increase the voltage here, you can see the current that's drawn from the power supply is increasing. Now this voltmeter here and the yellow trace on the oscilloscope are both measuring the output voltage of the power supply, and the blue trace here is measuring the voltage across the shunt resistor on my electronic load, so that's also proportional to the current that's being drawn. So first of all, I would say let's see what happens to the output voltage of the power supply as we crank up the current. So the power supply is set to 10 volts and we are reading 10.003 volts, which is pretty much spot on. And let's see what happens as we increase the load current. So I'll just turn this up slowly until we get to just under 3 amps. 2.9, that's good enough for me. And you can see the voltage here dropped to 9.984 volts, so that's about 20 millivolts drop from the previous voltage. So what this means is that as we increase the current to about 3 amps, the output voltage on the power supply dropped by about 20 millivolts. According to the specs of the power supply, the load regulation should be around 2 millivolts plus another 4 millivolts at 10 volts output. So that's about 6 millivolts maximum, but we're seeing 20 millivolts drop here. Now this is actually due to the measurement setup in a way, because we are measuring the output voltage at the binding posts, whereas the internal feedback comes from before the binding posts. So this extra drop in voltage that we are seeing here is most likely due to the ohmic resistance between where the feedback is done inside the power supply and where we're actually measuring it. Unfortunately, there isn't much we can do about that because the power supply doesn't have any inputs for external feedback lines, so that's just something we have to live with, I suppose. Now let's turn up the current even further and see what happens when we reach the current limit. Now, as you can see, the voltage dropped to about 2 volts, which is to be expected because we're trying to draw a lot of current, and this is now just limiting to give us 3 amps. If you listen very carefully, I'll just do it again, you might be able to actually hear a relay click as the power supply goes into current limiting mode. Now this relay doesn't have anything to do with current limiting or constant voltage mode as such. It's just to do with the way the regulation works inside this power supply. In order to keep the power dissipation on the pass transistor in here as low as possible, there are several transformer taps, and these relays are used to switch between them. And the idea is that you choose a transformer winding that gives you as low a voltage as possible at the input of your regulation, so you're burning as little power as possible across your pass transistor. So you can see that if I change the output voltage from say 9 to 8 volts, you can hear that relay click as well. So the reason why the relay clicked when we went into constant current mode is because the voltage dropped as we went into current limiting mode. And there's nothing really wrong with that approach as such. The only downside is that if you have a load that draws pulsed currents, you can go into current limiting mode regularly, and it also means then that your transformer taps are switched regularly. So what this means is that if you draw, say, current pulses, every time you draw a current pulse, the relays in there might switch, which isn't great for the life of the relays, and depending on how the power supply is designed, it might also not be that great for the power supply. So in order to have a look at that, I've got my signal generator up here, which I'll now just hook up instead of the constant voltage input, and we can have a look at how the thing behaves under pulsed loads. Right, the generator is hooked up and running. We are drawing current pulses of about 2 amps for length of 100 milliseconds every 2 seconds, and we can see that on the oscilloscope here we have a nice current pulse which is 100 milliseconds long and about 2 amps in amplitude. And if you zoom in a bit at the edge, you can actually see here the output voltage dipping a bit until it settles again when the control of the power supply has caught up. So now let's see what happens when we go into current limiting mode with our current pulses. For that, I'll just change the amplitude here to 2 volts, which means that I will be drawing a current of about 4 amps. And you can hear now the power supply is clicking its relay every 2 seconds, coinciding with the current limit kicking in. And the waveforms on the oscilloscope are quite a bit more interesting now, so let me just get this in shot nicely. Let's move this a bit over here. There we go. A bit bigger, yeah. So let's have a look at this waveform and try and figure out what's going on here. As you can see, our load current turns on almost immediately, and you'll see it actually is drawing the 4 amps that we're setting for quite some time until the current limit of the power supply actually does kick in and everything drops down to 3 amps. Likewise, the output voltage does remain at 10 volts for quite a bit, and then we have this linear slope going down until we hit our 2 volts, which again is the steady state for the current limited output. And this slope here is really due to the output capacitors of the power supply. Like almost every other bench power supply, the Keithley does have capacitors across the output terminals, and what's going on here is that when there's no load, those capacitors are charged to 10 volts, and then we are starting to draw 4 amps from the output, which these capacitors can of course easily supply. And what's happening is that actually from this point onwards the power supply is already current limiting, and the power supply is supplying 3 amps into those capacitors, and we are drawing 4 amps from those capacitors. So in net effect, this slope here is the capacitors discharging at 1 amp being drawn from them over time until we hit the 2 volts here. And if you're really keen, you can try and work out the value of the capacitor used inside the power supply. All you need for that is this slope and the net current drawn from the capacitors. And you can get this slope by just doing some measurements on the oscilloscope, like so. And you can see that this slope is about 3.3 volts in 486 microseconds. And if you plug those numbers into your calculator, you end up with a capacitance of just under 200 microfarads. And if you look inside the power supply, sure enough, there are 200 microfarad capacitors in parallel at the output. And those capacitors are also the reason why it's usually not a good idea to use your bench power supply as a constant current supply unless you're very careful with the way you set up your output voltage. Because what might happen is you will have your output capacitors charged to a certain voltage, then you connect your load and those capacitors will discharge into your load without actually being current limited for that period of time. So I think that's pretty much it for this video, because I don't really know what else I could do with this power supply for now. Initially I was actually hoping to be able to do a bit more digging on the stability and accuracy of the power supply, but to be honest, from what I've seen, the accuracy seems to be pretty much spot on, and I had it running off camera on the full load for about half an hour and nothing at all happened to the voltage. So stability also doesn't seem to be a problem at all, which is really good, especially considering that I had some concerns about the way the set point was generated, but apparently Keithley do have that very well under control. So yeah, if you can think of anything else that I should do with the power supply, please let me know. But from my side, I think that's it for today. Silence.